Make it fast.
Oh,
Yes.
Lavaux? Okay, close enough. From the University of Waterloo, and he's also a senior national fellow and a postdoc at Berkeley.
Yeah, it's for several applications.
Oh, yeah. And you did his PhD at IIT. And he's been talking to us about stuff.
Yeah, so it's going to talk about my favorite subject, some aspects, and mostly did my PhD on studying cosmic flows on the local universe. And now on, so after some break, I continue this work, but from another point of view, I will show in the presentation. So I'm focusing on cosmic flows. That means that I'm looking at large-scale structures. I'm looking at how this big batch of galaxies are moving, but on large scales. Not like how they move on small scales, like for example to form these clusters here, well, how they move inside the clusters here and form, for example, in redshift space, this kind of thing that you see here in the Datasets survey. And so why do we care about specular velocities? Well, there are basically the reasons. So if you look into a general universe governed by general relativity, you have for first order this kind of relation between the velocity field and density field. And this tells you several things. At first, you're going to be sensitive to intermediate scales. So if you look at a small patch like this, and this small patch is going to be sensitive to 100 megaparsec scale. So even if you take like this region here, you see that the velocity is on the side of, let's say, 5 megaparsec. It's going to be sensitive to all this matter that is around here. Second, you're sensitive to absolute matter content. You see that here the mean matter density is entering. You're sensitive to the growth of structure. So how is gravity actually? So this is this F factor that is actually telling you about here. And velocity field is much more linear quantity in terms of dynamics, which means that you can go back in time much more easily if you want to be interested in initial conditions of our local universe in terms of primordial perturbations. And that means that you can study the early universe in our local universe. So, well, I will talk, of course, about two velocity fields all the time. So, observed velocity field and predicted velocity field, depending on whether you start on this side of the equation or this side of the equation. So, a direct practical example of what I just said for testing gravity here is if you look at this F factor. So, it's a work that is recent and interesting by Michaelson and Torvald about if you look at this product F sigma H, you can look at different results of the survey. So here is a Wigglesy survey, here is VVDS, the BOSS survey, and SDSS large-scale structure surveys. Then you can measure this thing at different moment in the time. So it's a measure of the amount of the amplitude of specular velocity at this different redshift. And if you put furthermore the constraints that come from the green map, you actually may constrain the what is the gamma factor. So here, for example, it constrains that it should be within this band, and this is the lambda CDM classical factor at approximately that. So here, so far, it's not sufficient to constrain really heavily the gamma factor, but it's in good shape. I mean, much more than a few years ago. So this is a good motivation to look into this for probing particle modified gravity. So I will talk about essentially two subjects. So one is concerning the reconstruction of specular velocities. So let's state what I mean by reconstruction and how to apply it onto observations. And the second part on how to do kind of similar measurements but using the kinetic sinusoidal bridge effect. So this time on the CMB. So what I mean by Fourier reconstruction. So first, how do you observe specular velocity in principle? So the good old way is to use the, for example, here, so it comes from this relation, so where you have the Doppler effect on on one side, but that you measure directly from the spectrum of one galaxy. And here is the distance that derives from distance indicator, the Fisher relation on CITA, so the separate reconstructions and other indicators. And the residual of these two numbers is the vector velocity that enters the first order for the local linears. So of course, you have three problems. You have only a few galaxies because it's still relatively expensive to get this distance indicator. It's noisy, really noisy. It grows as roughly like 20% of the distance. So, for example, at 100 megaparsec, you have 100% error on the velocity, which is not good. And you have only one component for 3D velocity. So there is people have taken two different approaches to this problem. So one approach, which was the important method, was to try to extrapolate this velocity field to a 3D velocity field by some assumption on that the velocity is potential, for example, so it derives from the scalar potential. And it has been tried, and with some mild success, I would say, even some failure, because they were predicting omega naught equal 1 at some point. And then when it was really not 1, then they revise the method and they say, yeah, it's not 1, it's 0.3. So it's noisy. And prone to biases if not done correctly. The other approach is to do a prediction. So you start from density field and you try to predict the vector velocity field. And it's much more stable in that case because it's less noisy than, it's like if you have a noisy field and you take the derivative, then the result may be random. But if you have the velocity, some noisy field and you integrate it, then you have something that is smoother. So this is exactly the same thing for velocity. And then you can do velocity comparison with your observations. So it's a much older method because it essentially comes back to the tables in even before 80s. And then the least action method in 89 and microconstruction more recent. So I will focus, so if you have questions, of course, feel free to interrupt. So I will focus more on this part of the prediction part. So how does it work? Well, you start from a catalog of redshift of galaxies. And of course, you can infer the redshift positions and luminosity for all of these galaxies. And you inject this into a reconstruction algorithm that I will discuss. And you get reconstructed velocities. And then you can say, okay, let's study these reconstructed velocities. It's already interesting that there are a lot of dynamics that have been removed. And, for example, give you access to the initial conditions locally. Or you can do also a comparison to this observed velocity that comes from distance catalog of galaxies. And from this comparison, as I showed you, you can get some cosmological parameters or constraints on the gravity. So there have been several methods. So let's say linear theory, which is fast and relatively simple to understand. So you have the velocity field is proportional to gravity. It's the first equation that I showed. It has only one solution, but it's kind of approximate. It has some issues, for example, in clusters where it completely blows clusters of galaxies. And second is the least action principle, or the least action method. That essentially is negative gravity. So you start from the galaxy now and say, okay, flip the sign of gravity and push everything back in time. And so of course, it's like doing an n-body simulation, so a simulation back in time. So it has all the same problems. And it has also an exponential number of solutions because when you start, remember that you have only the redshift coordinate of the galaxy, which is a mix between the velocity component and the position. So you have to choose between several solutions sometimes, and actually it grows exponentially. But in principle, it's somewhat exact because you try to push back all your galaxies. It's exact up to the point where your galaxy actually are splitting. So instead of merging, because when you go forward in time, galaxies are merging, but if you go backward in time, they are splitting. So this part is not bothered by the least action principle. A third way is kind of in between. So you start from the continuity equation, that is the conservation of mass, and you impose some assumption on the dynamics, and you can end up with only one solution, relatively fast, and exact on large scales. So what is this assumption? Schematically, it looks like this. It's as taking that your trajectories of galaxy are not going to cross. So if what happens in simulations, and we call that matter simulation, and you see that in phase space, your trajectories of particles are crossing and forms like spirals and things like that. But if you may assume that it's not the case, then you can simplify a lot the problem. And this is, for example, what schematically it gives. Even if your trajectory is like this, you can model it like this by a straight line. Mathematically, it boils down to this. So if you mix that, so you don't have shell crossing, it's like stating that your displacement field, so how you map this distribution, homogeneous to this non-homogeneous distribution, is given by a convex potential displacement field. So you can find a scalar field such that you have a vector field that maps the two together. And you end up with this equation, which looks like Poisson equation, except that it's non-linear here. It's a determinant of the action of the potential, which is related to the ratio of this density field versus the homogeneous initial density. And the unknown is this phi. The good thing is that, this problem, which is also complicated, can be solved into this problem, which is a minimization of essentially a chi-square, a huge chi-square, and which is equal to the number of particles in the system. And so it looks like an inertial least action principle. And then you can solve this equation exactly. And if you want to solve this problem, so you have displacement field, and you want to transform this into a velocity field. And this is where the same factor that I showed at the beginning intervenes, that transform this translation here into a velocity field. So this is the other parts of the dynamical modeling. So this is called the Lavaux approximation. So this is the inertial motion approximation. So if you test this on n-body, you have this kind of results. So let's say that you run an n-body simulation of a patch of universe. You end up with, starting from primordial fluctuations, you end up with this density distribution, for example, to some scale. And this is the amplitude of the velocity field in this same slice. If you do linear theory, you have this kind of velocity field from the density field. So it looks the same, but here it's a bit rough on the edge, I would say.
Is there some smoothing, or is that just a direct?
There is a very, very light smoothing here. If you do the same thing at the same smoothing scale, with the Mach reconstruction, you get this kind of velocity field. So here you see that there are no big white patch here that indicates that you strongly overestimate your velocity field. And essentially you have all the topology of the velocity field. Even in this part here that is low velocity corresponds to empty area, you're really good in. I mean, you really get all this fuzziness here that you have here. And not over smooth like here. You see that it's slightly over smooth compared to here. So essentially, except in a few cases, so for example, here also when you are slightly biasing towards lower velocity, and here where the structure is not exactly the same and corresponds to clusters of galaxies, so where you don't have, your assumption is not correct, then your velocity field is correctly reconstructed. So there is made estimates on the statistics of the error. So typically you're off by 40 km by second. So for our velocity field that is of a few hundred km by second. So I applied this method to the 2 mass ridge survey. So the 2 mass ridge survey, so it's at that time was limited to 11.25 in K magnitude, and it's a full sky redshift survey based on the 2 mass photometric sample. And as you see, there is only the really low galactic latitude part that is missing. And for the distance catalog, I use the NDG3K, so it's a 30 megaparsec, very high quality distances for the nearby universe. So just to show you in 3D, it's a scheme of what's happening in the local universe. So we are at the center, and the color scheme is linked to the total luminosity of objects here, so the mask of redshift. So here it's cut at 30 megaparsec, the sample. And we have this typically the Virgo cluster. Here it's slightly in the direction of the beta factor region, so Ida Centaurus. And you see that it's really massive in that part and less massive here. You have like a void in that direction. So we're going to step a little bit backward. Here it's limited to 50 megaparsec, I think. So here you see all this part that is corresponding to the Ida Centaurus region that is really crowded. This is called the beta factor, because historically that's when people started looking at the velocity field, you see like an attraction of the local group in that direction. Here you have, on the other side, you have normal, and on this side you have another big guy. It's a precious Pisces supercluster located at 50 megaparsec. And if you step back again, so here it's limited at 100 megaparsec. So here you have the Great Wall area, to be here. So here is Coma supercluster. Here is the Hercules, and here is Octopus supercluster. And here you really go in the far outskirts of this sample. So you see that it's very sparse now. It's 150 megaparsec, and it's not really sampling this region that is called the Shapley concentration. So all the action will be in this volume. So this is the reconstructed specular velocity field using the Mach reconstruction method within this slice. So you see that the precious spices, so that I said, so the Virgo, the coma is here, the beta factor region, and we are at the center, so approximately here. And you see that all these flows are behaving as expected. I mean, they attract the massive clusters are attracting all the matter that is around here, and you clearly see a void empty area here that is acting as a repulsive point for the velocity. So now, oops, yeah. So now we can make a comparison. Let's say that we do a reconstruction in a 100 megaparsec volume, and we only the comparison on objects on 30 megaparsec. And we have to do this because of boundary effects. Otherwise, here the comparison will be affected by the fact that we don't put any structures here. So the flow will be incorrect. And in simulations, it happened that it was, in principle, 100 megaparsec was sufficient buffer region to be less affected by the boundaries. Up to what I call here the bulk flow, which is the global motion of this 30 megaparsec bubble, which is of course sensitive to scales that are much larger than 100 megaparsec. So if you subtract this bulk flow, that is the motion of this 30 megaparsec bubble, both in reconstruction and observations, you get this scatter in the velocity field. So here it's observed velocity, and here reconstructed, and the slope is giving you the omega matter, as I showed. So it's F factor. So an error bar is typically, well, in agreement with the real map, which is good. Not necessarily expected given all the noisiness and things that happens in this data.
How do you handle the selection functions of the density is dropping off with distance?
Yes. So the selection function of the two-mass space survey is okay till 50 megaparsec. So it's fairly nearly complete.
So for the 30 megaparsec, it's still...
Yeah. And it's relatively reliable up to 100, but not after. So it's the selection function is accounted for in the reconstruction, but you have this boosting effect. So whenever you're missing galaxies, you put the mass that you don't see in observed ones to preserve mass, the overall mass in your sample. But of course, that means that you're biasing your velocity in the edge. So of course, you have another observation, which is the CMB dipole. So you see this, it's our motion, the motion of the observer relative to the CMB. And you can do a number of transformation of the rest frame. So you can go to the solar system rest frame, to the galaxy rest frame, and to the local group rest frame composed of the Milky Way. So I don't remember which one. I think it's Andromeda and Milky Way. And be interested in what is the motion of this local group with respect to CMB. Because this is a very good observation. This is the only really good velocity field that we have. It's a 3D component, actually. So what test you can do is try to do reconstruction in deeper and deeper samples. So let's say that you try to reconstruction at 30 megaparsec, and you get, and when you look at velocity field at the center, you get this 300 km per second in that direction, and the CMB is in that direction. You can increase the depth. So you look at the same velocity, you get 400 km per second. You can increase 450. Here it sounds becoming suspicious. 150 megaparsec is 500 km per second. Okay, so it seems like you see an increase in the amplitude of the velocity of the local group that you put at the center of your reconstructed volume. So in terms of amplitude, it's okay with respect to the observed velocity. But in terms of angle, you see that here it goes well to 0, but it goes back a bit up here to 40 degrees. And here it's a limit at 95% for lambda CD and W05 cosmology. So actually, these points are perfectly okay. So here is okay. And one last thing. Here is the orbit of the reconstruction method itself. So here it should actually go in this part here of the plot. Unfortunately, these points here are not going. So what's happening? So there are two things that may happen. So one thing that you may note is the selection function. Well, you start missing a lot of galaxies around here. So the M-star galaxies are starting to disappear at that distance. So you can say, okay, the cutoff is incomplete. Forget about this point. Another thing is, okay, maybe it's not entirely the case. Let's look at what's happening if you try to understand it more quantitatively. You can transform this program of the velocity local group versus the CMB in terms of velocity of the bubble that you selected. So, for example, the 30 megaparsec, 50 megaparsec, etc., with respect to the CMB. And so, in principle, it should go to 0 because if the CMB rest frame, well, the CMB is supposed to be at rest, if the CMB, the fluctuation of CMB are supposed to be the same as the fluctuation that gives us all large-scale structures, there shouldn't be like a large gradient of density, so you don't expect to have different rest frame between the CMB and large-scale structures, so it should go to 0. The problem is that if you do this, the same kind of issue, so it goes down here and then goes up and stays there at 400 km per second. So this kind of suspicious size, can you understand that here you can have a larger error? So here it's typically the incompleteness error without self-level. But here it's in between and maybe there is some signal. So and that's there have been other works that actually look at this problem from different point of view. So there have been this, so this is my measurement here at 100 megaparsec in this direction. At 65 megaparsec there was not many things, but it was not seen also either in previous work, so it was pointing in that direction. And at the same scale, so Watkins et al. Used the direct distance catalog, so they tried to infer the bulk flow just by looking at distances. And they found also a bulk flow of 400 km per second in that direction. And the last one is very, very suspicious because it's it's a measurement using the kinetic sinusoidal effect, but the claim that there is a flow of 800 km by second at 300 megaparsec. It's really unclear because of discussion on the error bars. So typically, the authors argue that they have small error bars, but the rest of the community, like we know, it should have like 100% error bars. So, but still, we have at least two possibilities here for real workflow in that direction. What it means quantitatively is when you look at my data points at 60 megaparsec, well, the 1 sigma control here is englobing double not pi, no problem at all. And if you go to 1 megaparsec, which is the limit at which I'm trusting data, you get the sum tension of 1 to sigma, so really like not so much. So, I mean, there is maybe something, maybe it may be just pure fluctuations. But it's nonetheless interesting. So that means that we got interested in looking at whether there is a real possibility of measuring bulk flows at deeper distances using the kinetic sine-Lavaux effect, which will be a completely independent probe compared to all these distances redshift reconstruction. So it has been attempted by Kashlinsky, but for a cluster. And what we have been trying to do is to use the kinetic sine-Lavaux effect on galaxies. So how does it work? Well, just a quick reminder. So the kinetic sine-Lavaux effect is actually a constant scattering of the primary CMB photons on electrons that may rise in hot plasma that you can encounter in whatever structure that you have in linears. So typically clusters of galaxies or galaxies itself. And if you have, for example, an electron that goes away like this in bulk, then you will have a decrement in temperature in the same direction. And if it goes towards you, then you have an increment of temperature. So the idea is the following. So let's say let's take a galaxy redshift survey. You assume some electron density around galaxies and some velocity model. So here would be really basic model like a bulk flow. And you can make a KZ template out of this. And you fit this to CMB data, and from this fit you get bulk flow. And then you can start, okay, now I have this nice number, can we compare it to Baker velocities that comes from galaxy distance surveys, and you can check for agreements, or even, interestingly, whether you can measure the amount of variance in your samples, so like galaxies. So, unfortunately, there are a number of effects that may contaminate your signal. So, for example, the TLZ is happening in clusters with roughly the same distribution, so it's proportional to the number density of electrons times temperature of these electrons. The KZ, so it's the number density of electrons times the bulk velocity of these electrons. And the point sources in the unresolved point sources in your CMB sky acts as number density of galaxies times the frequency dependence of your point sources. So you have to check whether you may have this because, for example, you may have, like, I don't know, radio long galaxies or things that are very bright and radio in your galaxy, and you don't want to contaminate your KZ signal with this. So for these three things, so we use cluster samples, so galaxies and galaxies. And for this three, so we use the RBC catalog, so the Reflex BCS CITA catalog, which is a full sky cluster survey up to like 300 megaparsec. And the 2M++ galaxy combination that we just described, which is a catalog that I made with Michael Sun, that is deeper than the 2-matrix survey. And for point sources, we use the 2-mass extended source catalog for tracking the position of point sources on the sky. So the 2M++ is a new compilation made essentially. Okay, so we redid the catalog from scratch from the photometry itself. So we started from the 2-mass photometry catalog, and we populated it with redshift that we knew about slow digital sky survey from the 6DF. So slow digital sky survey is in the cap here. the 6-year galaxy redshift survey, which is here, and the rest is populated here by the 2 matrix survey. So it's essentially a true magnitude limited galaxy sample. In this part here, it's limited at 12.5 in K-tan, and in this part here, it's limited at 11.5 in K-tan. And it gives this distribution of galaxies. So it has like nearly 70,000 galaxies up to 200 megaparsec. And this is the 3D distribution. And it's a lot more crowded than the previous catalog. And also you see much deeper. So here I think is the Shapley concentration, which is much more clearly visible than previously. And but the thing is really neat is that, for example, you don't see the Sloan wall, which is just at the edge of this detection. With another 0.5 magnitude, it could be possible. So we use this, and the basic problem is the following. So we have a CMB sky given by double map. It's a mixture of several things. So it's typically the primary CMB that we don't want, the KNT standard LLH that we want, and the 2 other things that we are mildly interested. So the amplitude of the thermal standard LLH effect that may happen at the same position as the KZ for clusters, and point sources that are filling up the whole sky. And all this stuff are big by double map instrumental resolution, and plus instrumental noise on the screen. So, just for grants, yeah, of course, I forgot to write it here. But it's, I fit for it. So this is in terms of equations, so just to show how it works. So we essentially write a big vector that is a composition of all these terms, and we analytically marginalize according to the CMB fluctuations. So this is an example for one channel, but one frequency channel, but we treat the 3 frequency channels at the same time, using a variant of this, not exactly this equation, but a variant. And we are interested in this AKI and AT plus all the foregrounds that I haven't shown in this expression, because there are 20 or 25 terms. And the best fit can be computed analytically here in that case for a fixed power spectrum of the CMB. And we extract this scalars here.
What are your templates?
What?
What are your templates? Oh, your templates are constructed from your...
Yeah, so the templates are... So yeah, that's my next slide. So the KZ template is built on top from a model, an isothermal model for galaxies, which is as fair as it could. As it can be for galaxies, and normalized according to the weak density of variance in the universe. And essentially, the temperature is behaving like this. So there are a number of interesting terms here. So the KZ essentially decreasing the distance. Well, because just the galaxy is becoming smaller and smaller in the sky. Here is the galaxy velocity that we want to fit. Here is the fraction of free electrons that we assume to be 1, but it may not be. So that may be an interesting thing to fit afterwards. And if you compute this, you get this kind of template. So this is for an non-way. So here I just show back. Here is what I call the velocity weighing. So if you don't put this term here, you have this kind of and it's normalized to 100 km by second. So to show you that it's very small signals, so this is 10 microkelvin for so it's 10 microkelvin for 100 km by second, I guess. Yeah. And the noise for double map is in, well, it depends on where you're looking at, but it may be in 100 microkelvin. So, and the CMB is also maybe in 100 microkelvin. So you're looking at something a factor of 10 at least below. And you have foregrounds, of course, that are like factor of 10 above the CMB. So we did this fit. So There is not much signal, so that's the first thing. But there is a little bit of signal. So the TSZ is well fitted, so it's here even it's a Gaussian mask, but there is it's exactly 14 sigma, so there is no problem with the TSZ interval. For the KSZ signal, there is a little bit of signal. It's at the level of for 200 megaparsec of 9% projection of zero signal. So there is 91% that we caught something. And this is the direction. So we try two things. First, of course, the TSZ is present, we take for it, but the model may not be completely adequate. So we were worried whether there may be a residual at the TSZ positions that may bias our TSZ signal. So in that case, we so this is with TSZ not mass. So this is 50 megaparsec bit, 100 megaparsec bit, and 200 megaparsec bit. And here is by masking the TSZ, so it's roughly the same answer. Here it's of course a bit wider because we have less pixels. Of course, so before continuing, so there is one problem. So I say that here it's 200 megaparsec, 100 megaparsec, but it's a cut in redshift depth. Unfortunately, when you look at the sky, you have the projection of it. So you don't know exactly what you're measuring as a bulk flow. You measure some velocity, but you don't know what exactly the volume in 3D of it that is measured. So it's the problem of this estimator. So whenever you fit for it, this is the bulk flow part, and we'd like to know what is the statistics of it. So if you do linear theory, for example, for the velocity field, you can compute what is the covariance of this velocity field. Say, okay, you have a filter, you smooth your velocity field, I don't know, with a Gaussian or something like that. And you get the covariance matrix for it. And this typically tells you how, this is like a transfer function, it tells you how fluctuations on all scales in the universe are transformed through window function into your fluctuations of the velocity field at our point. So is it possible to find the equivalent for AK? So this is like what is the statistics of this estimator? So this is possible. So it's a complicated formula. It has a number of terms, but there are two interesting things. So here it takes into account the CMB weighing, so the fact that you have to forget about the CMB, well, the primary fluctuation of the CMB. And the second thing is here you have the 1 over d squared weighing. So that means that whenever you measure your bulk flow, it's like minimizing the bulk flow of the galaxy due to the vector velocity of the galaxy, but by affecting a weight of 1 over r squared to each of your galaxies. So it means that you're way toward the center. So it's an interesting information. It looks like what you encounter in distance catalog. You have the same kind of dependence because your noise is increasing as a distance. So it's like a weight that is decreasing as 1 over distance. Anyway, so if you compute this window functions, you have this kind of functions. So when I say, for example, 50 megaparsec, and you look at what's corresponding in terms of statistics, it looks like a Gaussian of 19 megaparsec, essentially. So it's like you smooth your velocity field at 19 megaparsec. And if you take 200 megaparsec, it's like 31 megaparsec. And it's taking into account the means of WMAP and the CMB fluctuations. So now we can say, okay, now we know more or less what we measure. So essentially, if you take a 50 megaparsec top hat KZ signal, so you cut abruptly at 50 megaparsec, your template, you get this answer. And you have to compare it actually to something that is more 20 megaparsec Gaussian, or more or less 50 megaparsec top hat, because they are equivalent. So, but the overlap for these two are okay in terms of direction. You see that they are in 1 or 2 sigma maximum. They are pointing in the same direction as the sky. So this is good. can you do it in terms of amplitude and quantitatively? So that means that, let's say that you take your bulk velocity that you obtain from distance catalogs, and you can transform this in terms of predicted KZ sigma if you trust this velocity that comes from distances, and up to some factor that comes, for example, from the fraction of free electrons. And you can also make a chi-square. So this is your predicted value, and this is your observed value from the KZ sigma. And you fit for this F factor. So if everything goes well, F should be equal to 1. So it means that you have everything is ionized according to the model, and the baryons are tracking the dark matter homogeneously compared to the mass of galaxies, so there's no issue. If everything goes really wrong, then it means, for example, if your galaxies are much more dominated by baryons, it may push this F towards higher values, up to a point where you deplete completely your galaxies of dark matter. So if you do this comparison with between one KZ sigma at 50 megaparsec and what CITA, so shallow, and SFI, so that are both limited at this distance of 20 megaparsec Gaussian, or with my value at 50 megaparsec top hat, which is equivalent. So you get roughly the same answer that points at approximately F of 1 point something, but it's compatible with F equal 1. And even if the KZ sigma by itself is not big, the ratio here in terms of this peak towards respect to 0, F, is above a factor of 3. So it is like you have some evidence in terms of Bayesian statistics that your answer is plausible by equal 1. So of course there is a lot of problems in this approach. So the profile is not entirely known because it depends on the integral value. It depends on this sigma squared here. It depends also where at what point you cut your profile. Stop at your radius or twice your radius. It depends a little bit, but not much. Depends a little bit on the shape of the profile, not much. We tried with an FW, it was changing a little bit. Of course, it depends a lot on the fraction of free electrons that you have to assume in the galaxy. And it's not dependent on the cosmic barons effect. We tried with several realizations in CMB, and actually, on the CMB spectrum, I mean, and actually sometimes we even got more than 2 sigma detection of KZ, so interesting. And the foreground, we made an extensive test, and we shouldn't be affected by it. So as a conclusion, so I showed you a number of projects and results that can be obtained from vector velocity. So they all boil down essentially to start from galaxy region survey and distance observations. So from the redshift surveys, we derive the KZ template, for example, that can compare to this distance observations with bulk flows and get this detection of galactic halo that in principle should be much more stronger with Planck, because the errors are expected to be divided by 3 for the KZ measurements for the bulk flow. From the redshift survey, from using methods of reconstruction, I show you that, okay, there are other things that are interesting to do that I haven't discussed, but from comparison with distances, you can obtain some parameters. And from the molecular velocity field, you can have constraints on large-scale power and the modified gravity. So thank you very much. If you have questions.
Okay, well, I think we'll just end there and have cookies upstairs and we can take a few minutes there.